All right, so we're going to practice our conservation of mechanical energy a little bit. So here we got a little picture here. We got a scientist sort of falling out of a tree, something like this. We're going to find out a couple things about the situation. First of all, let's give this guy mass. Let's say our scientist here looks kind of scrawny, so we'll say he's only 62 kilograms. And let's say that on the way down, at this point right here, let's say he's going 8.5 meters per second. And let's say he, start up here. Let's say he was 7.5 meters up to begin with. So as a location right now, we're going to find a couple of different things in the situation, but let's find a couple of things that are really, let's start with this. Let's find out what's his impact speed down here. So what's his final speed when he hits the ground? Well, that's not hard to do. Of course, when he hits the ground, it's all kinetic energy. And what we do is we piece things together. We know it's all potential energy at the top. The bottom, it's all kinetic. In between is a combination of the two put together. Now, if we use that idea at the very, very top, it's all right here. He's got potential energy. Down here, he's got kinetic energy. And of course, in between, he's got EP and he's got EK. And I know no matter which location, each of those should be equal to each other. So I know his mass, I know the initial height, so I can easily find out the impact speed at the bottom because the potential energy at the top is going to be equal to the kinetic energy at the bottom. So if I use that idea, the potential energy at the top has to be equal to the kinetic energy at the bottom. And the nice thing about that then is the masses cancel out, which makes sense because your mass has nothing to do with how fast you actually fall. So the final speed would then just be 2 times g times the height you started with, and then don't forget to square root it. So if we put that into the expression and we punched out, he's going at the very, very bottom, he's going around 12.1 meters per second. So down here, he's going 12.1 meters per second. There we go. Okay. So what about his location right there where he's traveling 8.5? Let's find out what is the distance he has traveled. So how far is he off the ground at that location when he's going 8.5 meters per second? Okay, well, there's a couple ways we can do this. I have his mass, I have his V, I can find his kinetic energy at that location. So at this location right here, his EK would be 1/2 mv squared. So I'll just do the 1/2. I've got his mass of 62. Now times that by the 8.5 squared, and I get a kinetic energy of round off a little bit, 2240 joules. Okay, so that's how much kinetic energy he has right there. But now, of course, he also has potential energy there. So if I knew his total energy at one location, then I'd have the total energy everywhere, which makes things easier. So I can do the total energy at the top, I can do total energy at the bottom. It doesn't make any difference. You'll get the same thing. So I'm just going to do the total energy at the top. I'm just going to do the mgh at the top. So if I do his mg times, his 62 times 9.81, and times that then by the 7.5, I can find that his total energy was about 4562 joules. And of course, the total energy doesn't change, it sort of just transitions. So that's his potential energy at the very, very top. And in between, we've got the 2240 of that is kinetic energy. So the remaining energy must be the potential energy. So if I subtract the 2240 from my total energy, his EP at this location is, give or take a little bit, it's going to be around 2320 joules. So pretty even. So at that location, 2240 of that was kinetic. The remaining 2320 was potential. So those two added up will still give me pretty much the same total energy I started with. So I just got to take this, make that equal to the mgh, and it'll tell me how much high, or the height off the ground. So I'll take that 2320 and divide it by his mass and by gravity, and we get a height of approximately 3.8 meters. So he would be 3.8 meters off the ground when he's going 8.5 meters per second. So then the distance up here, well, give or take just under 4 meters. So he's about halfway down, sort of in the middle-ish between where he fell from and the ground. Okay, so there's some basic conservation of mechanical energy. Now we can also expand on this a little bit. We can go to the bottom there and expand also like the work part a little bit. Of course, he's going to land and hit the ground. And suppose he goes into the ground, and when he lands in the ground, here we can even grab him here and like this. Okay, we're going to take him. We're going to get him into the ground, and suppose he squishes the ground a little bit when he lands. So let's say he comes down there and he lands and goes into the ground. Let's say maybe he compresses the ground 25 centimeters. So what force stopped him? Okay, well, this kicks into the whole connection between work and energy and that type of stuff. At the very, very beginning, we had about 4,500 joules of potential energy, and that transitioned into all kinetic energy at the bottom, and everywhere in between, it's a combination of the EP and the EK put together. But when he hits the ground, all that energy is taken away. The ground does work on him to stop him. Well, how much work does the ground have to do? Well, the ground has to do 4,500 joules of work to take away the 4,500 joules of kinetic energy he has. So to calculate the force is actually relatively simple. The force would just be the work divided by the distance. And the work that's done would be the 4562, because that's how much energy has to be taken away. The distance would just be the 25 centimeters, because that's the distance that the force is applied for. So all you have to do is take that 4562 and we divide that by the 25 centimeters, make sure it's 0.25 meters, and we get a force of around 18,250 newtons. Now, a couple things about that force. First of all, that would be the average force applied. Obviously, when you hit the ground, the initial force from the ground isn't going to be very strong, but it's going to get harder as you go. So that would be the overall general force, which is fine, nice averaged out. The other thing, the force, there's a couple ways you could look at. Some people would say that that force should be negative because slowing down. You could also say, the force is up because he's slowing down, something like that as well. There's different perspectives and way you can look at it. But the big thing is, you'd be around 18,000 newtons to stop him, and that would be an average overall force. And that's how, of course, the basic mechanical type stuff you guys are looking at connects to the work equals F, the expression that we started with in the whole work equals kinetic energy type section.